A student was doing an experiment to calculate the strength of a magnetic field. With me so far? Okay, so she suspends a conducting wire by a string attached to a sensitive balance and measures the length of the wire in the field. Right? So that's the L in F equals BIL sine theta. With me so far? She then passed a current through the wire and recorded the reading on the balance. So that'll be exactly how much force comes from passing the current through the wire when it's in the magnetic field. Right? So what other measurements will she need to make if she wants to find the strength of the magnetic field? We have a few options. The weight of the wire, the current flowing through the wire, both, or the force on the wire. So in this case, we're actually already measuring the force on the wire. That's what our balance is for. So it's not A. Now if we look at our equation, F equals BIL sine theta, we already know in this experiment that sine theta won't change, so we don't have to worry about it. We've already measured L as part of the experiment. We're trying to find B, so what we need is I and F, right? So that means that we need to measure the current flowing through the wire, that's the I. So our answer is either D or B. And as it turns out, if we want to measure F, then we also need to know the weight of the wire. So our answer is not D, but in fact B. You see here that B is the correct answer. Normally questions like these are accompanied by a diagram or something like that to make it a little easier for you. Question 15, last question in this section. What is the direction of the resultant force on the semicircular section, that is this middle part, on the conductor? Up the image, out of the image, down the image, or the force is 0. So let's think about this. If we look at the direction of the force on each part of the wire, we can use the right-hand rule, just like this, to figure out that the force here is going down. The force here is going down. That doesn't really help with the semicircular part, does it? So if we keep using the right-hand rule at different points around the circle, we see that at the top, the force is going down. At the sides, it's going inward toward the middle of the circle. On the other side, it's going inward as well. And so all around the semicircle, the force will be pointing toward the middle of the semicircle. So to find the total force, all we have to do is add these up. Now we can see that the ones going right and left will cancel each other out exactly. And in fact, the left and right components of these two forces will cancel out as well. However, the vertical component will not cancel out, so we'll still get a bit of a force pointing down. When we add up all the resulting down forces together, it's pretty obvious to see that the force on the semicircular section will have a net force of downward. So our correct answer is C, down the image.